starting with reviewing energy diagrams and actually looking at measuring stuff on them. So the changes in substances' properties or change in different substances requires an exchange of energy. That still, pertains here. And then the rest of the topics here are going to fit this enduring understanding. The energy exchange in a chemical transformation is required to break bonds and form bonds, okay? So we're going to be looking at those essential understandings. But for the energy diagrams, what do you really need to have to do? Be able to analyze and interpret, be able to find delta H and activation energy, and determine if they are endo or exothermic. For Hess's law, okay, new topic, this is a way of calculating delta H. You're going to explain, be able to explain that the relationship between enthalpy of a chemical or physical process and the sum of the enthalpies of the individual steps, okay? And be able to calculate the enthalpy of reaction using Hess's law. Now, the other two ways we're going to be looking at here for calculating delta H today is enthalpy of formation and using bond enthalpies. So there's in this particular PowerPoint, we have 3 different ways of how we're going to find delta H. There is a 4th way, and that has to do with calorimetry, which will be the next set of notes. Okay, so explain the exchanges of energy for different systems, solutions, reactions, okay? Write the reaction that corresponds to the following enthalpy changes. We have heat of formation, heat of combustion, heat of solution. They are specific to those particular processes. And then, okay, if it doesn't fit one of those particular categories, then in general, we usually just go like heat of reaction. Or if it is a phase change, it'll be like heat of vaporization or heat of fusion. So the little subscript is kind of telling you which type of process is occurring there. So we're going to use bond energies to calculate delta H of reaction with this equation. The bonds broken minus bonds formed, okay? And last but not least, to do the bonds broken, bonds formed, we use the dot structures to count the bonds so that we know that we're calculating correctly. And then we can figure out delta H from there. All right, so enthalpy of reaction or delta H, remember, reviewing here, little things, the difference in the energy of the products and the energy of the reactants, because this is a state function. We're looking at the final state minus the initial state, okay? In general, when you have to write out the equation, this is probably the quickest, easiest way to do it, okay? The one on your formula sheet is a little bit more cumbersome and it adds more variables to it, but if you when you have to write out the formula first before you substitute, I would use this one, okay? All right, sign for delta H is negative for exothermic reactions, and the reactants are going to be higher than the product lines when we're looking here at our enthalpy. And if it's positive, for endothermic reaction, you have a higher amount in your products than you do in your reactants, the amount of potential energy that you start with in the bonds, the stored energy, okay? Oh, sorry. Everybody good? All right. Now reviewing the diagrams and going back over, we're going to add in one more little factor here, the activation energy, which is that red arrow. On the left, we have the endothermic, where energy is being absorbed into the system. As I said before, the reactant line lower here, the product line is higher. So when you subtract, you get a positive delta H. On the right here, the reactant line higher, product line lower, so that means when you do the subtraction, your delta H comes out to be negative. Now, delta H is labeled as the difference in energies. Activation energy, EA, that's the abbreviation for activation energy, is the amount of energy needed to break bonds in the reactants to get the reaction started. And it's designated here on the graph as being the difference between the potential energy, stored energy, and the reactant bonds to the top of the transition state. The top of the transition state goes all the way up to the top of the hill, okay, like so. So reactant line to the top of the hill, the peak, that is how much energy needs to be inputted into the system to get the bonds to break and get it started. Now what you should notice, if you look at both of our graphs here, the endo versus the exo, that the hill is a lot higher for the endothermic than it is for the exothermic. So inputting energy into the endothermic side, that hill is a lot more to surmount. Okay, so usually those reactions that are endothermic, you usually have to heat them because they need a large amount of energy. All right. Now, first kind of question that you might see with a energy diagram or energy profile. Something like this could easily be a multiple choice question on the test or the exam. So, we have AD reactants going to CD products. Which of the following best describes the flow of heat for the reaction? As you can see, the first thing I look at when I look at my graph is this endo or exo?
Exo.
Exo, I agree, because here the product's lower than the reactants to start. So here is the difference. Here's our delta H. Now, come over here through the line here. You can see it's going to be 20 minus 40. So how much energy is going to be changed there? 20 kilojoules. Now, this is the key part, and you have to pay really attention to the wording. If you don't pay attention to the wording, you can easily mark the wrong one. So it's between A and B because we figured out the difference is 20. But transfer to the surroundings or transfer from the surroundings? Going to the surroundings because it's exothermic, it's being released. So yes, I would go with A. That is correct. All right. Now, they like to have you draw them in the free response too. And usually they'll give you some kind of starting off point like here. So the dissolution of ammonium nitrate, NH4NO3, here breaks apart into its ions. Okay, this is how the ice packs are created. So water is mixed with the ammonium nitrate and then it starts to feel cold. Okay, it's getting cold and then you can put it on your injuries or your sore muscles. Okay, so it says using information, please complete the reaction pathway diagram shown below and label the products and the delta H. So over here we're starting with NH4NO3 as our reactant, and we're going to complete the profile as to how it looks. So I need to draw in the hill part, but what is significant is where I place my product line. Should my product line be higher or lower than my reactant line? Higher, good. So I would go like this, and then I'd make a flat line higher, like so. Then it also says to put in the product, so here I would write in my NH4 plus and my NO3 minus, okay? Over there. I guess you could just put a plus sign in there. I'll do that. So NH4 plus and NO3 minus, like so. And then you would get your point for drawing it in correctly.
And is it like higher because like if it feels like it's getting colder, then it's actually taking in energy?
It is actually taking in energy because you have to remember that key point about where the thermometer is and where we are. If we're watching a chemical reaction, the observer, we are from the surroundings perspective. So that means if the temperature is dropping to us, that means energy is being taken from where we are and being put into the system. So it feels colder to us because we're in the surroundings.
Thank you.
Yes. All righty. Oh, did I forget? I forgot to draw on delta H, didn't I? Okay. Let's draw on delta H. Here you draw on your delta H. Like so. And then basically has the exact same diagram that I just had there. All right, very good. Okay. One more. They could ask you a question like, what is the activation energy? So here, we're looking at the activation energy. What two key points do I need to focus on? Reactants and top of the peak here. So, Pretty easy now. 100 minus 40 gives you what?
60.
So 60 kilojoules would need to be inputted into that reaction. Like so. And they could ask this in a multiple choice question. They could ask it in free response, that kind of thing. Although the activation energy part and the Hill part, the transition state, we'll be addressing that part of the graph in detail when we get to kinetics, because that's where all the speed and how fast the reaction goes takes place. That's the pathway part. All right. Now we're going to talk about Hess's law. Heat reactions, especially if you don't have really good equipment that can insulate, make sure that the heat doesn't escape in the process, isn't always easily measured. You know, like I said, in our lab, to get good data. Oops, wrong way, sorry. There you go. However, we can estimate the delta H using the published values that were conducted and are published in our textbook. You can also find them in tables on the online on Google. These published values were done at standard conditions, which we'll talk about what that means, and you can get a good idea and calculate the delta H if you cannot really get good data experimentally in the lab, especially with the type of equipment that you have. Because even the ones we would use in the lab would be like styrofoam cups. They're pretty good, but they're certainly not perfect insulators. All right. So going from a particular set of reactants to a particular set of products, the change in enthalpy is the same, whether it takes place in one step or in a series of steps. So we can go, you could do the one step in the lab, or you could look up the stuff, find some of steps of the reaction to manipulate, cancel, and multiply, and you can definitely calculate delta H in this way. So, Hess's law states that if a reaction is carried out in a series of steps, the delta H of the overall reaction will be the sum, equal to the sum of the enthalpy changes for the individual steps. Okay, because delta H is a state function, the total enthalpy change depends only on the initial state of the reactants and the final state of the products. So the in-between, one step or two steps or three steps, that's like pathway stuff. We can do it whichever way we want to, and we will still be able to get delta H. Now, this example, I like this diagram, an example, because we have this overall reaction here of carbon reacting with oxygen to give you carbon dioxide. This part right here is showing you it happening in one step. This would be one step. Over here, it's showing you the two-step side. Okay? Now, one step gives you delta H of releasing negative 393.5 kilojoules. So, exothermic. Now, we're doing it in the two steps. They looked at the tables. They found two reactions in the back there that once you combine them and cancel them down, they end up giving us this overall reaction here. So if you took the carbon plus the oxygen gives you carbon monoxide. Carbon monoxide with the oxygen gives you carbon dioxide. Each one of them has their own separate delta H. But what you should notice here is because they both have carbon monoxide on either side of the arrow, these would cancel. The two 1/2 oxygens would add up to giving you a whole oxygen here. Then all you'd have to do is add these two together and you would get your delta H. So it matches the one step idea here. Okay? So that's just a way of using the math to get your end result and find your delta H if you can't experimentally determine it in the lab. All right, so example 4 here, we have this overall reaction. It's kind of similar. Nitrogen plus oxygen gives us nitrogen dioxide, carried out in one step. This one in particular, and a lot of these also would be difficult because a lot of them start as gases and end as gases. So to have the equipment to trap the gases and keep the gases, also, like I said, not usually stocked for a high school laboratory here. Two steps here though, we have nitrogen plus oxygen gives us nitrogen monoxide. It has its own delta H. nitrogen monoxide plus oxygen gives us nitrogen dioxide. The first step, as you can see, is endothermic. The second step is exothermic. We can add them two together. They're already set up to cancel, which is nice. Like so. And then all you would do to figure out the overall delta H is add them together. So 180 plus a negative 112 is still going to give you that 68. So one step or two steps, doesn't matter. Okay, and these examples I've been showing to you are simple ones because they are already set up to cancel, which is nice. Not all of them will be though. All right, but if they're not ready to be canceled, we can do some things to make them cancel. One of them is reverse the reaction. To reverse the reaction, all we have to do is change the sign on the delta H. Even though technically some of these are not really reversible like in nature, but mathematically and theoretically, we can still figure it out that way. So if you reverse one, just change the sign on the delta H. The other thing that we can do is, because heat is extensive, we can multiply it by an integer because we can add more amount, right? More reactants means more heat or more cool, depending on which way it is, if it's endo or exo. If you multiply by a coefficient to get your mole ratio in the balanced reaction to be correct, you also have to multiply the delta H by that same coefficient, by that same integer. So, because it's extensive, we can multiply. All right, now, this can be trial and error. Some problem-solving strategies for you. You can work backwards. I'm going to show you kind of how I approach these problems. You don't necessarily have to do it my way, but you can work backwards from the reactants and products to decide how to manipulate them. You can reverse any reactions, and you can multiply reactions. Okay? So, for example 5 here. We have these two steps, and we're looking for this overall reaction. Okay? That's what we want. So, the first thing I do is, of course, take a glance at it. Going, okay, what are for my overall reaction, I'm looking for nitrogen. I'm looking for water gas. I'm looking for oxygen and ammonia. So, I just usually start left to right and go, okay, so nitrogen. Here's nitrogen. Look at my two steps here. Nitrogen's right here in the first step. Then I ask myself, is nitrogen on the correct side? Is it a reactant? No, it is not. So I'm going to need to flip this one. I'm going to need to flip it. Now, the other thing I ask myself is, does it have the right coefficient? It's 1/2 N2, but I need it to be 2 N2. No, it's not. So I'm going to have to multiply. What do I need to multiply this one by? So everything in here gets multiplied by 4. So I'm going to flip and multiply that way. Now, okay, next, I look at, say, okay, H2 is not in my overall, so that one's probably going to cancel. O2 is in my overall, but it needs to be a product. So what am I going to do here to the second one? I have to flip that one too. And here it's only 1, but I need it to have 3. So I'm going to need to multiply it by 3. So everything, including the delta H, gets multiplied by 3. So take a moment to flip them and multiply through. Alright, we flip them, we multiply through. Take a moment to do that. Okay, so after you flipped and multiplied them, it should look like this. Hopefully you have them set up where you have 2N2 plus 6H2 giving you 4 ammonia. Your delta H was changed to a negative and multiplied, so it's 184. Negative 184, that is. The bottom one should be 6 H2O, water vapor, 6 hydrogens on the products, 3 oxygen on the products, and then your delta H becomes positive because we flipped it, and because we multiplied through, it's now 1452. The next step is what you want to do here is cancel, make sure everything lines up. So, nitrogen, nitrogen, that one's a check, that one's in the right place. Water vapor, check, in the right place. 3 oxygen, check, in the right place. And the ammonia, yes, they're in the correct place there. Now, as you can see, you have 6H2 in the reactants in one, 6H2 in the products in the other. So that means these guys cancel out, and they're gone. And then all we have to do is take these and add them together, right? So this ends up being delta H is going to be 12 something, 1268 kilojoules. Very good. Like so. Now, not all Hess's law problems only have 2 steps. Some of them have 3, some of them might have 4. This particular example has 3. So, once again, I mean, you can work it however you want to. I'm just going to start, and this is what I'm going to do. I start with my very first reactant here. That's ethene C2H4. And I'm like, where is that? The only one I see it in happens to be the 3rd step. It's right here. It is not on the correct side, so I'm going to need to flip this one. And that's what I do, then I flip it. So, I don't need to multiply though because it does have the correct moles. My delta H though becomes negative 52.3 kilojoules. The next thing though that I do is then I look at F. Well, I see F2 in 2 places, so I'm going to wait on looking at the fluorine. I'm going to look at something else where it's not in 2 places and see if doing other things with the 2 products will help work out the fluorines. So, next one then, I'm going to look at this product here, CF4. Okay, CF4 is in the products here for the 2nd step. It needs a 2 in front of it, though it doesn't have a 2. So this one, I'm going to need to flip and multiply by 2. So that's what I'm going to do. Flip that one, multiply by 2. Oh wait, sorry, you're right. I'm not needing to flip that one. It is already on the product side. Thank you. Okay, so I just need to multiply by 2 then. Thank you for correcting that. Okay, so just multiply by 2, we need 2C plus 4F2 gives us 2CF4. And multiply by 2, this is going to be negative 1360 kilojoules. Yes?
Multiplied by 3 since there are 6 moles of F2.
Once again, there's F2 in 2 of the series, so I'm going to hold off on that one till the end. So if I multiply 1 by 3 and it gives me 6, there's still a 7th in there. So I would wait to do those ones at the end if there's multiple ones in the series. So then I look at HF. HF product. HF is also in the products. I don't have to flip that one, but in my overall it's a 4. So I do need to multiply this one by 2 as well. Alright, so multiply by 2, so 2H2 plus 2F2 gives me 4HF. Delta H then becomes what? Negative 1074. Alright. Now I look for canceling and hopefully it will work out. So I check here. Yes, check. The F2s, guess what? It worked itself out. I have 4 in one and 2 in the other. That adds up to 6, right? This is going to be 6 F2s. So that one's good. Here we have that. Yes, the CF4 and the HF. They're in the correct spots. Okay, make sure everything else cancels. 2 carbons go. 2 hydrogens go. And yes, now we're just ready to add all this up. We add all this up and we get anyone? 1,486. Sounds good. Kilojoules. Yes. Now, one little minor note on the significant figures. Remember, when you're adding, it's about place value. These two go to the ones.
I got 2486.
2486, I believe, is the correct answer. So check your numbers again. These two go to the ones, though. This one goes to the tenths. When you're adding, you go to the place value. So in this case, you would want to go to the ones. That's why we would not put the point 0.3 in there. Negative 2486 is the correct answer. So now for practice 1, I want you to go ahead and try one on your own. All right, looking at this one, going to start here. Like I said, I always start here. B2H4, see that one here, it's in the right place. And it has the right coefficient, so this one just stays the same. Okay, now the Cl2s. So this one, Cl2s here, as you can see, that's 1/2. It is in the correct place, it's a reactant, we don't have to flip it, but we do need to multiply through, and in order to get 1/2 to 6, we get to multiply by 12. So this gets all multiplied by 12. And I'm going to just like cross this one out so I don't have to rewrite that one. And this is going to be 6H2 plus 6Cl2 gives me 12HCl. And then what is the new delta H for this one where we multiply by 12? Anybody get that?
1107.6.
1107.6. Thank you. All right, very good. Okay. Now, next one here, BCl3 right there. That is not in the correct position, and it doesn't have the right coefficient, so we have to flip it and multiply. So we're going to do that. So flip, multiply. So we do that, and we get 6HCl plus 2 of this boric acid stuff. And we get 2 boron chlorides, boron trichlorides, and 6 of the waters. All right, now, this delta H, what does that turn into? 225 kilojoules. It's positive because we flipped it. Okay, we changed the sign, and we multiplied by 2. So I'm also going to go ahead and cancel this one out. So I'm dealing now with these 3 delta H's. Okay, time to look for canceling. So waters go, and we have the 12HCl and the 6HCl. The 6HCl goes away. This turns into 6HCl. And the borac, the boric acid, those go. Very good. And last but not least, hydrogens go. So then we check to make sure it matches. That one matches. That one matches. That one matches. And this one matches. Good. We're ready to add. So we have the negative 493.4. And technically this is 0.0, by the way, because you keep the 10th position there. So this one will be rounded to the 10ths because all of them start off going to the 10ths. You add that up. This one, this one, this one, what do we get?
Negative 1376.
76.0. The delta H. There you go. Check.
Oh.
No, it's boric acid.
But I didn't even realize.
Boric acid is in
not.
borax, though, right?
I don't know, it might be.
Makes sense. Yeah, I didn't see there was a.
All right. Now, specific types, heat of formation. First type, where it has a separate designation. So they put delta H with the little F there. Okay, what does that mean? What does formation mean? Enthalpy change for the formation of 1 mole of a substance. Okay, now when we say formation, we're forming a compound or molecule from its elements. All right, from its elements, it's being formed. So, for example, what would it look like if I'm forming H2O, water? Well, forming water here, the water would go over here as the product because it's being formed. But by definition, heat of formation is for 1 mole of that, so we have to balance it off of the fact that this is going to result in 1 mole. Now, what are the elements that go into making H2O? And what are their normal elemental forms? Diatomic. So, hydrogen will be H2, and our oxygen will be H2. Now, this is, I'm sorry, O2. That is correct, O2. I wrote it down as O2 and then I said H2 out loud. Yes. All right, now looking at this, we have the 1 mole of water being formed. So you have to balance it off of that, and this is where it results in having fractional coefficients. And yes, they have to be fractional. That's the way they're represented. Do not use decimals. Okay? So H2 matches just fine, but for O2, what do we need to put in front of there? We need to put in 1/2. And now it's balanced. So the formations, as you can see, this is where they get fractional coefficients in these tables. You will also see that also result in the next example as well with combustion. However, before we do that, it's time to practice. So, forming from its elements, okay, make sure it's always 1 mole of the substance. Try to write out the reaction for forming a mole of methanol. Forming a mole of methanol. Write it out as the product. We're going to form it over here. CH3OH. That means we need what element first?
C.
Carbon. Is carbon diatomic?
No.
No, so you just put C. All right, the next element, H, which we know is diatomic, and the third element, which is also diatomic. So, add these in. Now to balancing. C's, do C then H then O. That's the best way to do when you have organic in order like this. H's need a what? 2 here, because there's 4 on that side, right? And for our O, we need 1/2. Very good. All right, heat of combustion. And yes,
For the, like, writing it down, does that have to be in the order of the molecule, like C, then H, then O?
no, not necessarily.
Oh, okay.
You can write them out, however, in whichever order you want. That's fine. All right, heat of combustion. You see it's COMB in the little subscript now. Similar to formation, the fact that this is about combusting 1 mole of the substance, right? 1 mole undergoes combustion. Now, undergoing combustion, though, you need to remember what the other things that are going to be in that reaction. What is the other reactant in combustion? Oxygen's the other reactant. Very good. We're going to produce carbon dioxide and water as our products, so keep that in mind as well. For example, if I wanted to combust the methanol, I would add in my O2 and my CO2 and H2O for the filling out the rest of the reaction. But do remember, it's going to balance off the fact that this stays at 1. So everything else gets balanced off of that, and that's why we have the 3 halves for our O2 there, okay? All right, so delta H for this reaction would be the heat of combustion, so delta H with the COMB for methanol. So try to balance what combusting 1 mole of benzene would look like. Take a moment to do that. Okay, starting out here, we're going to put in our benzene, O2, the CO2, and the H2O. Once again, much easier to start with starting balancing with carbon first, then do hydrogen, then do oxygen at the end. So what do I need here to balance my carbons? 6, good. What do I need here to balance my hydrogens? 3. So on combustion ones, then you add up the O's over here. We have 12 plus 3, that equals 15. So what do I put in front of my O2 to make that balance? 15 halves. Yes, there you go. I know it looks strange, but that's how it is done. Once again, these are for formation and combustion. Because it is defined as that, it has to be to 1 mole of that substance. So that's why we have to use fractional coefficients.
So now, from now on, like on the AP test, when we get combustion that isn't like the.
If you're getting just a regular combustion and they tell you to balance it, you would balance it normal. But what you're going to see here for these ones, these are going to be the ones that are in the tables, because they are done at 1 mole of that substance, so they always have fractional coefficients in them because of that, the way that it's designed. Because delta H is an intensive property because it's this much heat per mole of the whatever, okay? So it is an intensive property like density, so keep that in mind. All right, so the last one, heat of solution, SOLN, the designation. This is described as the molar heat of solution. Compound shows 1 mole of the compound dissolving in water. All right, so when compounds dissolve in water, like NaCl or the ammonium nitrate one that we saw with the potential energy diagram, when they dissolve in water, 3 things take place. You have the ionic bond has to break between the 2 in the salt. That's endothermic. Have to break the ionic bond. Then you have to disrupt the hydrogen bonding IMFs in the water. That is also endothermic. You're overcoming some of those forces. The last part of the dissolving process is when the water attracts to the ion and surrounds them. Remember, the H's point in towards the anions and the oxygen parts of the water point in towards the cations. They form that ion dipole force. That part, the formation of the ion dipole force, is the exothermic part of the process. So you have 2 that have to be, broken or overcome. You have 1 forming, and out of those 3 together, whichever one nets the highest, of course, determines the overall reaction. Dissolving, magnesium sulfate. I don't know if you guys know this, but that's the stuff that's in the heat warmers, the hand warmers and feet warmer stuff. Okay, that is exothermic. So when it dissolves and reacts, it will technically it's physical process, but we do have forces and bonds exchanging here that changes over in the heat. The other example already presented in this one is the ammonium nitrate. That one's obviously endothermic because that's what's in ice packs, so it ends up feeling cold. So keep that in mind about the dissolving process. There's a lot going on there, and we're going to talk more about this because we're going to be doing heat of solution problems in the next set of notes when we look at the calorimetry stuff. So 3 processes taking place in dissolving. Have to overcome bonds and forces, and then we have to form the ion dipole force. Now, writing reactions, of course, is out of 1 mole of the particular salt that's dissolving. This is basically stuff you've already done. We've already written out the dissolving equations in the last unit, so let's just refresh our memory. Sodium chloride, pretty easy. We know what's the charge on sodium. +1, the one on chloride, -1. So we're starting out with NaCl solid here. Okay, NaCl solid. It's now going to dissolve in water. We're going to get Na+, that's AQ, plus Cl-, that's AQ. Sodium chloride's easy because the ions are 1-to-1 with the formula unit. So remember, this is basing this off of the idea that this part is the 1 mole, but the formula units always start out as 1 mole if they're dissolving, okay? The ammonium phosphate is slightly different though, because ammonium phosphate, what is the charge on ammonium? +1. What is phosphate's charge? -3. So our formula unit looks a little bit different to start with because we have to have 3 ammoniums for every 1 phosphate, like so. Basing it off of the idea, of course, one of these is dissolving. When it breaks apart over here, how many ammoniums are we going to get? 3 ammoniums that are going to be AQ. So the ammoniums are going to be triple the concentration of the phosphate, right? Because you get 3 dumped out for every 1 formula unit. And then the phosphate, you're just going to get 1 each time. When you're doing these, though, make sure that when you're splitting them up into their ions on the right, that you have to include the charge in the formula. You can't just write PO4. Because PO4 and PO4 -3 are 2 totally different things. So make sure you include your charge there. Okay? So sodium chloride and ammonium phosphate. All right, so for the problem set though, I'm just putting this public service announcement here. They're going to take place in standard states, and we're going to talk about what standard states are in just a minute, but problem set, sometimes they'll give you the table of values in the problem itself, but sometimes it doesn't give you the table of values and you have to go to the appendix to look it up. And these are going to be found in appendix 2B. It's like A5 to A10, and you can go to your table of contents in your e-text and find that really quick, you know, throw it up in another tab so that you can go to those pages where it has your delta H's listed for you to use. So yes, you might need that for the problem set, just giving you fair warning. All right, definition of standard states. What is a standard state? Now you're going to notice that a lot of the reactions from here on out, they're going to have 298 next to them, K, or they're going to say 1 atmosphere or something next to them. So what we consider standard state for a compound is 25 degrees Celsius. Standard conditions, okay? Not standard temperature is 0 degrees Celsius, 273 K. That one we use, you know, in gas laws and stuff. But standard conditions, like sitting in the lab when they're trying to make up these tables, they were doing at what we would consider room temperature, which is about 25 degrees Celsius. Now, for gas, the standard state, or assumed standard state, is 1 atmosphere, which is the atmospheric pressure at sea level. That's the reference point there for that. For a solution, if it's considered to be at standard state, it is a 1 molar solution. That is the concentration by definition. And if you have a liquid or solid, it is considered to be pure substance, not a mixture. Nothing is in it besides that particular chemical. Now, when we're talking about elements at standard states, we are talking about, like, how does the element exist at 25 degrees Celsius at 1 atmosphere? So nitrogen at 25 degrees Celsius in 1 atmosphere, it happens to be a gas. Like all the ones on my periodic table over there that have the green symbols, even though that periodic table is based off of 30 degrees Celsius, those ones are gases at standard states. However, the liquids though, bromine and mercury would be the only ones that are liquids at standard states up there on the periodic table, because the temperature is a little bit higher, so the other ones that are highlighted in blue, I'm assuming they would still be solids at 25 degrees Celsius. Pretty much the rest of the table though, you can see exist as a solid in their standard state, which is 25 degrees Celsius, 1 atmosphere. Okay? Going back to another thing to note, what you'll see in the symbol, anytime it's in standard state, like delta H, they put a little degree thing next to it like so. So later on when we get to other ones, like there's delta G, if they have a little degree symbol next to it, you know that's the delta G at standard state. Okay, you're going to see other ones. There's delta S too, delta S, entropy, Gibbs free energy. But anytime it has this little degree symbol next to the symbol, you know you're at standard state, which is 25 degrees Celsius, 1 atmosphere. Or if it's a solution, it's 1 molar, blah, blah, blah. Okay? So that little degree symbol tells you something as well. All right, now enthalpy calculations. Change in enthalpy for a reaction can be calculated from the enthalpies of formation of the reactants and products. Now, this is the complex one, like I said, that's on your formula sheet. But if you have to write out the, because I require you to write out the formula before you substitute, that's very cumbersome to write. So really, I think you should just stick to, you know, sum of delta H of the formations of the products minus the sum of delta H formation of the reactants. Really, that's acceptable to me to write it that way before you substitute. The other one tells you some other stuff in it, but I'm just going to assume that you know you're multiplying it by the moles in the balanced reaction before you're putting it in there. And I guess I should state, everybody knows what the large sigma there with the E looking thing means. That's the sum of, right? They use that in math a lot. Everybody knows what that symbol means? Okay. Just checking. All right, one other thing to note too is elements in a chemical reaction where it's in their regular element standard state, they do not have heats of formation because they don't really form from anything. They just exist naturally. So their heat of formation is 0. We have heat of formations for compounds and molecules because you're actually combining elements together to make them. Now, I only say that too because, like here in my table, I gave you the fact that hydrogen is 0 and sodium is 0 because they're elements. Sometimes, though, in the problems that the AP will give you, they'll only give you the table with the water and the sodium hydroxide, and they're assuming you already know the others are 0. Okay? So just be aware of that. Now, heat of formation method of finding delta H is not difficult. It's really a plug and chug. Plug it in and calculate and get it out. So this is the second way that we're calculating delta H. The first way was Hess's law. Now this is the second way using heats of formation. We're going to calculate delta H. So we write out our formula here, right? Delta H products minus the sum of the delta H formation of the reactants. So product, first product here, I use brackets too to keep my stuff separated here. We have 2 moles of the sodium hydroxide being formed, so we're going to multiply our sodium hydroxide value by 2. We're going to add it to the other product. The other product happens to be 0. You don't have to necessarily put it in for your work. You can just cross it out if you want to. You don't. 0, adding something to 0 is going to be that same number anyways. So that is these are our products here that we've taken care of. Now it's minus our reactants. So water, 2 times the water value, negative 286. plus the sodium, which is 0 because it's elemental. And technically you would do 2 times 0, but 2 times 0, of course, ends up factoring out. These two end up factoring out. So they're not really necessary to have in our reaction. Then all you have to do is do the math. But be careful with the signs because you're subtracting. And a lot of times your second one over here to the right is going to be a negative number and you get the double negative. Don't forget to make it plus plus. Or you'll get an incorrect answer. So 2 times 470, this is going to be negative 940 minus, and 2 times 286, negative 72. So this ends up doing the plus plus here, and our overall delta H is going to be what?
Negative 386.
Negative 386 kilojoules.
I thought it was 68.
Oh.
I'm sorry, 68. I wrote down 68. Didn't say 68, but I wrote down 68. This is kilojoules technically per mole reaction, but I think you can put kilojoules without the per mole reaction, still be okay. And remember, per mole reaction means like 1 time of that reaction running. So that would be 2 sodiums, 2 waters, gives you 2 sodium hydroxide and 1 hydrogen. So this is the delta H. Notice some things you can tell about it. What type of reaction is this way? Exothermic. It's giving off heat, okay? Because delta H ended up being negative, we know it's exothermic. And you might need that, context clue later on in the FRQ. So, as you go down and it hops to a different topic. All right, easy enough. Now, this is the only other type of problem with the heats of formation. This is where they give you delta H, but you have to find one of the individual components. Okay? So they gave us the heat of reaction. They gave us they gave us one of the products. They gave us both reactants. But now we have to find the heat for this guy, for water. Except for it's not water, actually it's water vapor in this case. And what you're going to notice too is this number is not going to be the same as the negative 286 on the previous problem, because water in the previous problem was actually in liquid phase. This one's in gaseous phase, so those numbers are not going to match. And then we'll talk about why they don't match after we calculate. So remember to, of course, write out the equation first. Sum of delta H formation products, delta H formation reactants. All right, then we put in our delta H over here, plug that in. Okay, starting our products, 4 times NO, which is 91.3, plus 6 times whatever this is. So I just put it in as the compound. I put that in as the variable. All right, and then we're subtracting out our reactants here. We have 4 for our ammonia. So 4 times 45.9 negative, don't forget the negative. And lastly, oh, this is easy because it's elemental oxygen, so 5 times 0, but we don't really need to put that in. That does not matter. Now it just becomes algebra. So, but just be careful because you don't want to get your signs mixed up. So this is going to be 0.2 plus 6 times the water minus a negative, this is 183.6, is that right? So then we do plus plus here, combine these like terms, all right, move stuff around. Alright, so that we end up with just our 6 waters, isolate that. And this, I'm getting negative 1450.8 equals 6 times the water amount, so we divide by 6. And we get for the delta H formation for our water ends up being negative 241.8 kilojoules per mole. So, this is, of course, for the gaseous phase of water. Whereas the delta H formation for our liquid water, if you remember from the previous slide, was negative 286 kilojoules per mole. Let me tell you why those numbers are slightly different. The gaseous one's releasing a little bit less energy than the liquid one is in that formation of the water. Both instances, you're forming OH bonds, 2 OH bonds to make water. That's the same for both. The difference is in the phase now. So when you're forming liquid water versus gaseous water, you also have to form hydrogen bonds, forming IMFs to hold it together to make it a liquid. So that's why you're releasing a little bit more energy, because in addition to forming the OH bonds, the covalent bonds, you're also forming IMFs. So that number is slightly going to release more energy, forming bonds and IMFs versus just forming bonds. So that's why the phase does really matter there. I just want to point that out. Alright, so these are the 2 types of heaps of formation type problems you'll see. So we've done Hess's law, heaps of formation, and now we're on to bond enthalpies. Bond enthalpy. So let's review what we need to do to have a chemical reaction. 3 things have to happen in order for us to have a chemical reaction. Reactants must collide. This is collision theory. They actually have to bump into each other or you're not going to get any bond breaking. They also must collide with the correct orientation. They have to hit the correct side of the molecule in order for bonds to break. And they must collide with enough energy, and that energy is the activation energy amount, or you will not get the bonds to break. So, collision theory, we're just referring here because we're talking about bond enthalpies, we're going to be referring to bonds breaking and bonds forming here. So, and yes, later on, when we get to kinetics, we'll also watch the nice, cute little TED Talk video about how to get to date for the dance and how you can learn how that helps you speed up a chemical reaction. Yes, that's a very fun video to watch. It's in here if you want to watch it before then, you're welcome to. But for our purposes, we don't need to know all that just yet. All right, so the atoms in the reactants, they break and they're going to rearrange. So in this process of the chemical reaction, we have 2 things occurring. Let's review those and then we'll call it a day. All right, bonds have to break. Bonds have to form. So reactants, the bonds break. Products, the bonds form. Now, just remembering, and we've already talked about this, but going back to this idea that energy is required or absorbed to break bonds. So breaking bonds is endothermic. Overcoming forces, breaking bonds, anything of that sort goes under the endo category. And we say axing is taxing because that, you're like chopping wood with an axe. Axing is taxing. Of course, it's requiring energy. Last but not least, energy is released when bonds are formed or IMFs are formed. Forming is warming. So forming process is always considered exo. But do remember, in a chemical reaction, you have both processes occurring. So whichever one is higher is what the end net result is going to be for the overall reaction.